Hi everyone, my name is Zhewen, and I'm pleased to be here to get this opportunity to present our work, Norma, a high-performance network load tester, which is done by Nanjing University, cooperated with Alibaba Corporation. As we all know that network load tester is one of the most important testing tools. It is designed to generate high volume traffic, high volume of network traffic, and measure the resulting impact on the devices under test. This test traffic can be configured by the operator's test task. For example, if we want to know how much throughput our load balancer can afford, sorry about that. We can configure the tester to generate random port UDP traffic and then measure the input rate. And then the tester accepts the test task and generate our expect traffic to the load balancer. And the load balancer will then process the traffic and forward it back to the tester. So finally, the tester can measure the input traffic and to get the throughput of the load balancer. Also, based on the measurement, there's many other aspects can be evaluated by using the tester, such as package loss and latency. Therefore, a network load tester is indispensable for daily network operations, such as performance monitor, failure troubleshooting, and stress testing. Let's take a look at the two types of devices that we commonly tested. The first one is the fixed function devices, like switches and routers. These devices are not generally capable of reprogrammed and to do other stuff and to perform different functions. The second one is a programmable devices, like P4 programmable switches, net FPGAs, and the servers with network functions software. These devices can be programmed to customize their behavior. So what function we want for a tester? First, fixed function devices support high throughput traffic, so our testers needs to be generated the same throughput traffic to fully test them. Second, programmable devices may have complex network functions such as TCP connection, filters, and load balancers, so our tester should be able to support stateful protocols and customize package headers. Also, our testers should be able to precisely control the traffic it generates in terms of the rate and the burst. Finally, the tester should not only generate traffic, it must measure the traffic accurately. With that, we can use the tester to diagnose our devices. Existing testers can be classified into these four types based on the way they generate traffic. They have their own advantages and disadvantages in terms of throughput, programmability, and the cost, but none of them can fully meet our needs at the same time. Software testers use the CPU to generate traffic. For them, generating traffic at a terabyte level per second for testing traditional switches is very CPU intensive. And the net FPGA-based testers use FPGA to generate traffic. On the common net FPGA platform, there are only one to two network ports. So use it to test 32-port switches and other net devices is too expensive. And the commercial testers generate traffic through hardware provided by the manufacturer. The testing functions they offer cannot be fully defined by the user. And one of the recent work called Hybrid Tester also proposed a tester based on the programmable switches, but it cannot support stateful protocols like HTTP TCP. Therefore, we decided to build a practical load tester to satisfy our requirement. So here is Norma. Here, let me introduce Norma to you guys. First is the pipeline for the programmable switches ASIC can provide us the hardware basis to support high-throughput traffic generation and package header customization. And then the Norma's architecture illustrates how our testing functions are arranged and implemented in the switch. And due to the time constraint, I would like to focus on the approach to implementing the stateful protocol on the programmable switch. So how to support a stateful protocol? In general, this is like letting a programmable switch to emulate a protocol program. This program can be written as a state transition table. For example, the switch is going to emulate TCP client, and it receives a same packet, and it is got its flow state ID, which is 0. Then the switch looks up the state transition table, and the table knows that when it receives a same packet and its flow state ID is 0, it should trigger a SYNACT packet and write the next state ID, which is 1 back to the flow state ID. But because of some limitations on the hardware, this state transition table is not as simple as I talked before. So for example, the flow state cannot be accessed twice in the pipeline because of the program switch pipeline structure. So we have to loop the package to work around this limitation. We need to loop back the package. And at the same time, the switch limits the maximum header length that can be added. It means that it is impossible to directly add a 1,000 byte payload to a 64-byte packet. So we have to prepare a batch of large package looping in the pipeline at the line rate first. Then tells the looping packet what to do with a queue. The looping package will pull the queue, and then we'll know what action should be executed then. And after executing the action, the switch sends the packet out via multicast. So this is the whole picture of the Norma's stateful responder component. Based on this, we add many other test functions to build a practical tester. First is the classifier. This is the component we use to classify the input traffic. We needed to distinguish the traffic that whether it do need to be respond as a stateful responder or not. And also we need the measurement modules to measure the traffic as the input and output. The tester also needs to control the rate of generate traffic. So we added a rate burst controller to control the rate and burst pattern of the output traffic. Here we can achieve the rate and the burst by the design of this component, which is detailed in our paper. Users may also request to configure the packet fields of the generated traffic, such like random destination IP addresses. So we need we need a packet editing module to modify this package. Implementing these modules in Norma will encounter many difficulties. I would like to leave these details in the paper, but I believe we did pretty good. Next, I will show you the usage of Norma. Norma has been used to test pre-online devices for over 2 years in Alibaba, and we have presented one real usage, testing a load balancer in our CDN system. In our testbed, it connects to the ISP network and 4 backend services with both 4 100 gigabyte links. To test the load balancer, we use Norma to emulate the traffic from both users and the backend services. Norma generates HTTP requests to the load balancer like the HTTP client, and then the Norma response to these requests returns them back to the load balancer like HTTP services. We change the connection establishing frequency by tuning the HTTP flow length. From the result, we observed that when the flow length was less than 1 megabyte, the throughput was lower than 80 gigabytes per second. This is because the CPU bottleneck will be encountered when processing the small flows, causing the HTTP connection establishing rate to reach the upper limit. And in this case study, we can see that with Norma, we can obtain the performance of our load balancer under various traffic conditions. Also, Norma gives us a reference standard for later optimizations. Furthermore, we can support potential bottlenecks before the deployment of our productions. Now I'm going to show you Norma's ability to generate traffic. We evaluate the maximum throughput of 3 typical traffic, including UDP, TCP, and HTTP. We expect that Norma can support a variety of traffic and achieve high throughput. All experiments conduct in 2 Tofino programmable switches, where one is a tester and one is the device under test. 2 switches were connected via 3200 gigabytes per second optical fibers, which provide 3.2 terabytes per second bandwidth in total. We first evaluated Norma's throughput of UDP traffic with different packet sizes. And Norma can generate traffic at the rate of at least 1.6 terabyte per second and reaches 3.2 terabyte per second for the package larger than 256 bytes. The rate of small packet generation is reduced due to the reaching the maximum packet processing rate of the switch ASIC. Next, we evaluated Norma's throughput of TCP traffic with different TCP push packet sizes. The results show that Norma can achieve at least 1.4 terabyte per second with 128 byte push packets, and near 3 terabyte per second with MTU size packets. And finally, we evaluate Norma's throughput of HTTP traffic by emulating HTTP sessions with different flow sizes. Theoretically, we expect that Norma can generate 1 terabyte per second HTTP traffic at most, and our test result meets our expectation. And in summary, we built a first practical network load tester used in production. Norma is able to generate high throughput traffic, control its rate and burst pattern as commercial testers. And moreover, Norma exploits programmable switches to support stateful protocol and package header customization, which is one of our major points. Norma has been used in our operation for 2 years in Alibaba and successfully detect many performance issues. And thank you for listening, and I'm ready to your questions. Thank you.